This is quite similar to the first problem that we have solved, but now, the crucial difference of that problem from the previous one is that there are now angles in here. So setup of the problem is like that. There is actually an incline in here, so let me show the side view in there. So that's the side view, right? That's there are two rails in here. They form an incline, and you just place a bar on top of them, and the bar can now slide down. That's essentially an incline problem, but of course there's an additional magnetic field in here which makes the problem a little bit more different than the typical incline problems that we have seen before, right? So as a result, let's just describe the essential points in here. There's a circuit in here, there's a closed loop, so the current is going to flow there, but the resistance is only in here. Why did I do this? Because otherwise the resistance of the circuit would be time dependent, because since this length becomes longer each time this thing slides down, that means that the amount of the current that passes over this circuit is going to change with time. That's kind of complicated and unnecessary. So therefore, I just placed the resistance at a single place in here. So as a result, at all times, the resistance of the circuit is R. It has the same value. So in any case, in that case, when I drop the bar on the rails, of course, there is no friction. Did I say? Yeah, there is no friction between the bar and the rail. So it's just starts sliding down. But after that, of course, there's this magnetic force start acting on, because of the induction, of course, there will be a current within the circuit. All right, if you remember that the magnetic force acting on the circuit acts like behaves like slowing down the motion. Let me just say it like this. I'm not going to say like friction, but of course it's more like friction because there's actually a dissipation of energy in here. But we are going to come back to the energy discussion at the very end, right? So as a result, there's a uniform acceleration, of course, if there was no induction. So then there will be a g sine theta acceleration downward. But of course, the bar cannot accelerate forever because there's an additional magnetic force which slows it down. So eventually, of course, the bar is going to reach to a terminal speed, and we are going to find this. And after that, I'm going to basically compute the essential quantity so that we can discuss the conservation of energy statement. All right, so that's the side view. I think I'm going to also use this one, but let's start with this one. I'm going to erase all the unnecessary things. So we know that there's a magnetic field upward. So let me erase everything in here as much as I can. So what we do in here is we essentially need to do some kind of a parameterization. So this, the length of the bar is equal to A. So that's given like that, right? That's A. I need this length. So I'm going to call this as X, and I'm going to measure it from the top, so that the area of the circuit in here, this area, is equal to X times A, and that's the time dependent one. So that the area is changing with time. How does it change with time? Well, I can take the derivative with respect to time. So as a result, that's going to give me the velocity of the bar. So dx over dt is the velocity of the bar in the parallel to the incline direction. So what else? I need to compute first the flux. So flux in that case is the dot product of magnetic field with the area. So let's just forget about this integral step, or let me just write down the integral step and then write down this thing in here. So since the magnetic field is uniform, I can simply write this thing down as the magnetic field multiplied with the area vector. So let's come back to this original, the side view picture. Let me also erase this magnetic field in here. So in this case, of course, the area vector is a vector like that. Just remember that the area vector is a vector which is perpendicular to the surface. So therefore, it is like that. So therefore, the angle between the area vector and the magnetic field is equal to theta. So it's the same as the angle between the incline and the horizontal. So therefore, the flux expression, so that's B dot A, so that's the dot product, that's equal to B times A times cosine theta. Right, that's the, in a way, the difference of this question from the previous ones, because we have a cosine theta factor in here. But the angles also come into place in some other places as well, probably. So let's go ahead then. So the flux is therefore equal to the magnetic field. Area was x times A, and we have cosine theta. Yes, I have chosen a direction, I guess. I have chosen a direction, right? Because I have specified that the area vector is pointing like that. It has an upward component at least, which means the direction that I need to use to measure the EMF is along that direction. So as a result, the EMF along that direction is negative of the time derivative of the flux. So in the flux expression, it is only the x quantity which is time dependent. So as a result, I'm going to write it down like that. And so therefore, this is equal to minus BVA cosine theta. So that's the EMF. There's a minus sign. So that essentially means that if I insert in the numbers in here, the magnitudes, I'm going to get a negative value for the EMF. So the EMF along that direction is positive. If you want, if you're not comfortable with a negative value of EMF, you can choose the direction in the opposite way. And so as a result, the EMF along that direction in the opposite direction would be therefore, let me call this as epsilon prime, that's plus BVA cosine theta. Let's use it like that. So let's just do it like this. So therefore, the current that's passing from here in this direction would then be, the current would be, that's on the value of the current along the direction of the green arrow is BVA cosine theta divided by R. Okay, so from the side view, we have a current which is coming towards us at the topmost point, and current which is going into the screen at the place of the bar. Right? You can think of it like that. So that's a positive current. All right, what else? So I think I'm going to go back to the incline view. So let me add a page in there, a clean page, so I can redraw this picture. So we have an incline in here, right? This angle is theta. We have a block, essentially. This is the bar. Right? We know that there's a... let me just draw the free body diagram in here. We have the weight force acting on it. There's a normal force acting on it. So let me just draw the force from here. There's a normal force. What else? There's a magnetic force too. So in that case, I need to remember the directions in here. So let me redraw some of the things. So green direction is the direction of the current, and yellow is the direction of the magnetic field. So let's remember that the magnetic force is F mag. Magnetic force is I times L cross B. Basically, L is into the screen and I is positive. So that means the magnetic force is in the rightward direction. So it's horizontally rightward. So that's F mag. All right, it's not like that. It's not opposite to the velocity, all right? So velocity is along that direction. Velocity is downward. So the magnetic force actually acts like in a way that it slows the motion. So, but it's not directly opposite to the velocity. It's just horizontal. That's reasonable because, of course, the magnetic field is upward, right? The magnetic force should be perpendicular to the magnetic field. So as a result, it's reasonable that it is horizontal. So it's just given, determined by the direction of the magnetic field. So in any case, the magnitude is current times the length of the bar is A, magnetic field is B. I need to place a sign of angle in here, so in that case it's 90 degrees. So this is IAB. I was using little I for the current, so let me correct this. Little I. What was I forgot again. I think this was BAV cosine theta divided by R. So therefore this is B squared A squared V divided by R times cosine theta. All right. So let's see what happens in here. I mean, initially, of course, let's say it like this. If you start from rest, in that case, the initial velocity is 0. In which case, there is no magnetic force. Magnetic force is 0 because force is proportional to the velocity. This is reasonable because induced current is produced by the induction phenomenon. So that depends on how rapid the change is. As a result, this induced current is proportional to velocity. And so therefore, the magnetic force acting on the bar due to the presence of the induced current is proportional to velocity. So at the initial time, of course, this is 0. So that means, of course, if there is no force slowing it down, so in that case, it's going to accelerate downward with an acceleration of g sine theta, right? Let's just do it like that. So at the initial moment, it's going to have a g sine theta acceleration in the downward direction. But of course, as it speeds up, the magnetic force will also increase too. So in that case, the acceleration in the downward direction is going to slow down. And of course, as long as there is an acceleration downward, the speed is going to increase further. But eventually, there's going to be a point where the speed reaches to its final value. So this is called the terminal value. At the terminal value, the acceleration is 0. So if you want, you can think of it like that. The velocity initially increases at a rate of g sine theta, but because of the presence of this magnetic force which acts in the opposite direction, eventually it reaches to a final value. So that's the terminal speed. Terminal speed. And we would like to find this basically. So the condition for the terminal speed is that the acceleration is equal to 0. So that's it basically. So in this diagram, therefore, let me erase everything in here except the free body diagram and the magnetic force expression. I erased almost everything. Right, so that's my box. This is F mag. Right, so that means the net force is equal to 0. Okay, so as a result, I need to write down two equations. How can I write it down? I think I'm going to do it like this. I'm going to choose a reference frame in here. Let's say it like that. So I choose the y-axis upward and x-axis in the horizontal direction. So I'm going to write the F net being equal to 0 equation, but of course for this I need to write down the x component and the y component separately. This is essentially the things that we have done in the mechanics part of the previous course. And so as a result, it's essentially these kind of things. So this angle is theta. So I'm going to write F net along the x direction. So I know that the magnetic force has a positive component which is equal to the magnetic force. The normal force has a negative component, so therefore this is minus n times sine theta. That must be equal to 0. And the y component of the net force is equal to, this is plus n times cosine theta is the component of the normal force, and minus mg is the component of the weight force. So from here we find that n is the normal force is equal to mg divided by cosine theta. Right, so it is the same at all times. And so let me continue from here. Sorry about this, or let me just pull this thing to somewhere else. So I'm going to move it in here. I'm going to need that expression. So basically I have two equations and two unknowns, and I just find these. So F mag is therefore n sine theta, so therefore this is mg times tangent theta. So when the magnetic force reaches the magnitude of mg tangent theta, the object, the bar, has reached to its terminal speed. So therefore b squared a squared v over r cosine theta is equal to mg tangent theta, which means the speed is let me write it down like this. This is mgr divided by b squared a squared sine theta divided by cosine square theta. Right, so the angle enters into the problem in many different ways. We also have the angles in the free body diagram as well. And because of that, we don't have just a single cosine theta factor that we carry around. So we have a little bit more complicated factors in here. So as a result, so this expression looks a little bit more complicated. So let me copy this. Okay, so then I need to discuss the energetics. So what happens, right, when this thing reaches to its final terminal speed? So that's the terminal speed. So at this point it is moving at constant speed. So to discuss the energetics, of course, we have to count all the forces and then compute the amount of the work done by them. Since we don't have a given time interval, instead I'm going to find the work done per unit time. That means the power. So this is one of the things that we can compute. So let me start with the resistor, the power of energy dissipated on the resistor. Power of, let's say, heat produced in the resistor. All right, so that's basically I squared R. What was the current? It was B squared A squared V over R times cosine theta. And this is resistance in here. Was it like that? No, it wasn't. No squares in here, but let me check in any case, because this is BVA cosine theta over R, yes. So this is the expression. So therefore this is B squared A squared V squared over R times cosine square theta. I think I need this equation now. It's in here. So let me erase these unnecessary things. So this is the terminal speed. I need to also insert this thing in here. So therefore this is b squared a squared over r. V squared is mg squared r squared b to the 4 a to the 4 sine square theta cosine to the 4th theta and then cosine square theta. Right, that's this part is within parentheses is the v squared, and let me check one more time if this is correct. It appears to be correct. So therefore this is equal to mg squared r divided by b squared a squared, and I have tangent theta squared. This is the power of energy dissipated on the resistor. Alright, let's. I need to also remember this, but I'm not going to copy this. So the next thing is the power of work done by gravity. Let me just say weight, the weight force. So in that case, right, let's draw the incline again. The weight force is downward and the velocity is along that direction. Right, let me not write any angles in here. So this angle is theta, so therefore this angle is 90 minus theta. So as a result, let's say it like this. This is the power of the weight force. That's basically equal to the force dotted with the velocity. Right? We take the dot product of the force with the velocity. The force has a magnitude of mg. The velocity has magnitude, which is the speed. And then we have the cosine of the angle between them. So this is 90 minus theta. This is essentially sine theta. So therefore, this is mgv sine theta. I need to remember what we have written down for the speed. Let me look at it and then write this thing down. So that's mgr. Let me try to keep this in mind. mgr b squared a squared sine theta over cosine square theta. All right, I didn't reserve much space in here. So as a result, this is equal to mg squared r over b squared a squared and then tangent square theta. This is the power of the work done by the weight force. All right. So you can see that the power of the work done by gravity is equal to the power of the work done by power of the heat produced on the resistor. Right, that's very reasonable. So what is the power of the work done by the magnetic force? Right, let's just clarify one of the issues in here. Are we computing the power of the work done on the bar, or are we computing the work done on the system? So by system, of course, we mean everything else in here, everything. So the rails and the resistor and the bar together. So that's the system, or you may just consider the bar only. So if you are considering the bar only, in that case, the magnetic force, of course, does work on the bar. But in that case, I mean, since the bar is not accelerating, you can actually compute that force. Let me actually go back to the free body diagram in here. Right, so this is the magnetic force, this is the weight force, and that's the normal force. and the velocity vector is pointing downward. So the sum of these three forces are equal to 0. So therefore, this implies that the power, let's say, transferred by these forces on the bar, therefore should be 0. We know that the normal force doesn't do any work because there's a 90-degree angle between the normal force and the velocity. Magnetic force does work, so it just does a negative amount of work. Gravity also does work. We have just computed. It just applies a positive amount of work. So you can see that the sum of the power of the magnetic force and the power of the weight force is equal to 0 in here. There's no problem with this. Okay, so I'm just considering the bar only in here. So I'm not considering the rail or the resistor within my system. But if I consider all of them together in here, if I consider the whole system, in that case, it appears that the power supplied by the gravity, which is basically directly transferred to the bar, but of course, the energy doesn't stay there, so it is transferred elsewhere within the system. So the power of energy transferred by gravity is equal to the power of energy dissipated on the resistor. So it appears that in that case, the magnetic force again doesn't do any work. Okay, so if I just consider the bar only, the magnetic force appears to do a work on the bar, but if you just consider the total system, somehow the magnetic force also doesn't work in here. So essentially, there is no energy transferred from the magnetic field to the system. We are going to talk about the energy of the magnetic field later when time comes. There is a certain chapter that we need to discuss this. But this is a problem where there is no such transfer of energy. So all the energy is basically supplied by the gravity. And whatever it is supplied, of course, it is essentially dissipated on the resistor. So from that point of view, the energy is conserved. So let's just repeat again. That's basically this statement in here. The power of the energy provided by gravity is equal to the power of the heat produced on the resistor. So therefore, the energy is conserved.